So here we're going to focus on another space that is naturally associated to an m by n matrix. So we're going to start out with a definition. So if A is an m by n matrix with columns v1 through vn, then we define the column space of A to be the set col of A, defined to be the span of the vectors v1 through vn. If we think about the column space as the image of the transformation T from Rn to Rm associated to A, then it is clear that the column space is a subspace of Rm. So this is not an unfamiliar space. We've been thinking about column spaces without actually naming them column spaces all along. So let's think about some of the things that we know. So we've already seen that if V is the span of some number of vectors, say v1 through vn, then the dimension of V is the size of the largest subset of linearly independent vectors. The largest subset of linearly independent vectors. So if we think about this in terms of matrices, this number of vectors that are linearly independent is the same as the number of columns of our matrix A, with columns v1 through vn, that have a pivot position. This is an invariant of a matrix, and it's an important one, and it's one we call the rank. So the rank of this matrix A is the dimension of the column space. That is, the rank of A is equal to the dimension of columns of A. Equivalently, the rank of our matrix is the number of columns of A that contain a pivot position. So when we discussed the null space of an m by n matrix, we observed that its dimension should be equal to the number of free variables in the augmented matrix. Well, of course, the number of free variables corresponds to the number of columns that do not contain a pivot position. This new vocabulary allows us to write down an important relationship between the dimensions of these two spaces. This is called the rank nullity theorem. So the rank nullity theorem says if A is an m by n matrix, then n is the dimension of the null space of A plus the rank of A. So let's go back through our examples from the last video. Our first example was the projection from R2 to R1, defined by T of xy is equal to x. We, of course, identified the null space with the y-axis, which is a one-dimensional subspace of R2. The rank nullity theorem tells us that 2 is equal to the dimension of the null space, which is 1, plus the rank of A. This, of course, tells us that the rank of A is 1. This tells us that the column space of our matrix A, which has entries 1 and 0 as its two columns, is a one-dimensional subspace of the one-dimensional space R. So, of course, that tells us that the column space is R itself. This, of course, should not be surprising. If you choose any real number A, you can always find a vector A, y, whose image or projection onto the x-axis is A itself. Our second example was a matrix with 3 columns, 1, 2, 3, 2, 4, 6, and 3, 6, 9. The null space of this matrix we saw was the plane spanned by the two vectors -2, 1, 0 and -3, 0, 1. So the rank nullity theorem tells us that 3, which is n, should be equal to the dimension of the null space of A plus the rank of A. So of course, being a transformation from R3 to R3, this tells us that the column space is a line. To see exactly how this is a line, we simply need to observe that the reduced row echelon form tells us that if we label our columns V1, V2, and V3, then we can write V2 as twice V1 and V3 as 3 times V1. This tells us that the column span, which is the span of our 3 vectors, V1, V2, and V3, is simply the span of V1, and there's our line. For our final example, let's go back to the 3 by 5 matrix A with the following columns. So we saw that the null space for this matrix, with columns which we've labeled V1 through V5, was 3-dimensional, and it was spanned by the vectors 2, minus 2, 1, 0, 0, 3, minus 2, 0, 1, 0, and 0, 2, 0, 0, 1. So of course, the rank nullity theorem tells us that 5 is equal to the dimension of the null space of A plus the rank of A, which is 3 plus the rank of A, so the rank of A must be 2. So of course this tells us that our column space is a plane inside of R3. To see exactly how to express this as a plane, we simply need to locate the 2 pivot positions in our matrix. These 2 pivot positions correspond to the vectors V1 and V2. So our column space will be the span of those vectors V1 and V2. To see this explicitly, we can observe that the reduced row echelon form allows us to write each of our vectors V3, V4, and V5 as a linear combination of V1 and V2. And of course, it's important to note here that this plane does pass through the origin because our column span is in fact a subspace of R3. So finally, we want to make a nice observation about the rank and the invertibility of a matrix. So let A be an n by n matrix. The matrix A is invertible if and only if the rank of A is n. So the proof of this proposition is simply a translation of several equivalences that we already know. The first is rank nullity. Rank nullity tells us that the rank of A is n, which we can write as the dimension of the null space plus the rank of A, if and only if the dimension of the null space is 0. But of course, the null space has dimension 0 if and only if the only solution to the homogeneous equation is the trivial solution. And of course, we know that this is true if and only if the columns of A are linearly independent. We know that the columns of a matrix are linearly independent if and only if every column contains a pivot position. And of course, because A is square, A has a pivot in every column, if and only if it also has a pivot in every row. But of course, this tells us that A must be row equivalent to the identity matrix. And finally, a matrix is row equivalent to the identity matrix if and only if it is invertible. And that's it for now on subspaces of RP.